Illuminated by IEEE Photonics is a podcast series that shines light on the hot topics in photonics and the subject matter experts advancing technology forward.
Hello, everyone, and welcome to today's episode of Illuminated. My name is Akhil, and as the past Associate Vice President for the Young Professionals at the IEEE Photonics Society, it's my pleasure to welcome you to today's episode. I'm a biomedical physicist and engineer working at the University of Strathclyde as a Chancellor's Fellow and a Leverhulme Early Career Fellow. In my role for the IEEE Photonics Society, I support and promote initiatives, much like this podcast, to raise the profile of valuable young professionals within various sectors. The Young Professionals Initiative is for graduate students, postdoctoral candidates, and early career professionals up to 15 years post their first degree. This affinity group within the Photonics Society is committed to helping one pursue a career in photonics. We're here to help evaluate your career goals, better understand technical pathways, refine skills, and grow professional networks through mentorship. Now, on to our podcast. In this podcast, we're going to discuss reconfigurable switching, phase change materials with our special guest and moderator. So our special guest is Winnie Ye from Carleton University and Rachel Won from Nature Photonics, who will be our moderator. In today's episode, you will hear from Winnie as we discuss her journey, her research, and her ventures, and we go beyond academia towards career and research advice as well. Today, there's something for everyone. Let me introduce you to our moderator before I hand you over. Rachel Won is an international editor for Nature Photonics. She joined the journal in June 2006 as one of the 4 founding editors. Rachel and I have met at many, many conferences before, so we know each other quite well, and we keep missing each other at conferences as well. Before that, Rachel worked for Aston University's Business Partnership Unit in Birmingham as a Medici Fellow, commercializing the university's research output with a focus on photonics research. She obtained her PhD in microwave photonics and nonlinear optics as a member of Aston's Photonic Research Group. She worked for Philips Optical Storage in Singapore as an optics engineer after completing her master's degree from Nanyang Technological University of Singapore, doing research in optical fiber sensing. She holds a bachelor's degree from National University of Malaysia. She's a fellow of Optica and SPIE, and is a wonderful, wonderful moderator. So over to her. Rachel, all yours.
Good. Thank you, Aki, for the very nice introduction about me. And also thank you for IEEE Photonics Society as well for having me today for this Illuminated podcast. It's my pleasure to be here. Yes. So welcome everybody to today's podcast, where we dive into the cutting edge world of reconfigurable switching using phase change materials. We will explore how these innovative materials are transforming electronics, the challenges in their development, and the potential they hold for future applications. So we will also discuss the unique properties of these phase change materials and how recent advancements could spark the next wave of innovation in this field. So I'm very excited about it. So I'm sure a lot of us will be very excited to hear more about this. So stay tuned for a fascinating conversation that bridges science and technology. So today we are very pleased to have our guest speaker, Winnie Ye from Carleton University. She's an elected board member of IEEE Photonics Society Board of Governors. So before we get into the details about the technology part, I would like to tell you more about Winnie. So Dr. Winnie Ye is a fellow of Optica and a fellow of the Engineering Institute of Canada, currently a full professor in the Department of Electronics at Carleton University. She's an expert in silicon photonics with application ranging from telecommunications, data communications, biophotonics, and renewable energy. Her outstanding contributions have been acknowledged through various prestigious awards, so including the 2021 IEEE MGA Leadership Award, the 2020 Partners in Research National Technology and Engineering Ambassador Award, the 2018 IEEE Women in Engineering Inspiring Member Award, and the 2018 Engineering Medal for Research and Development from the Ontario Professional Engineers. So in addition to these honors, she received the Provost Fellowship in Teaching Awards in 2019 and Carleton University Graduate Mentoring Award in 2022. So Winnie, currently holds the chair-elect position of the IEEE Women in Engineering for 2024, and she also serves as an elected member of the Board of Governors of the IEEE Photonics Society. What an impressive bio you have, Winnie, and welcome you today to be the guest speaker for this very interesting topic on reconfigurable switching using phase change materials. So it's our pleasure to have you here. I'm sure we would like to know more. So let's tell us more about this. So what are exactly phase change materials and how phase change materials enable reconfigurable switching? Winnie.
Yes, thank you so much, Rachel, for the wonderful introduction. It's my pleasure to be here. So today we're going to talk about phase change materials, PCMs. So PCMs are materials that can can reversibly switch between different phases, typically between amorphous and a crystalline state, which exposed to when you expose the material into with the external light, excitation like light, heat, or electrical currents. So these phase transitions can result in significant change in the material's properties, such as their optical reflectivity, electrical resistivity, and thermal conductivity. So what makes phase change materials suitable for reconfigurable switching applications is that PCMs have a bistable nature, meaning that they can exist in two distinct states, as I mentioned earlier, the amorphous and the crystalline state. And each state has each unique properties, basically. So the transition between these states can be super fast, reversible, and require relatively very low energy, making them ideal for applications where rapid switching is essential. Also, the contrast in the optical and electrical properties between the two phases allows for high performance modulation, which is critical in applications like optical communication and neuromorphic computing. So the durability and repeatability of these phase change transitions can further enhance the reliability and longevity of the devices utilizing PCMs.
Okay, good. So I have a question here that I would like to know more, because you said that you can use heating, right, to change the phase of the phase change materials. Does it need to be very hot? Because heat could be an issue, right, if we have it in the computer and devices.
Excellent question. Yeah. So it's not about the actual temperature. The actual temperature is not very high. But the thing is, we're talking about nanoscale devices, right? So when you focus in that small volume, the heat is extremely high in that spot. But if you're talking about energy that's applied to that heat is not very much. Yeah.
So it's not
that's why we talk about the energy efficiency of these PCMs, because you don't really need a lot of power to drive these devices.
Okay, so it's not really an issue like overheat or something.
Yeah, no.
Okay, good. So why is this technology significant for the future? I think it's getting more and more important. So why is it?
Yes, excellent question. So I think I can identify 4 areas that's very important in the future for PCMs. The first one is data storage. So PCMs will be, in my opinion, will be a key technology in the development of non-volatile memory devices, which are faster and more durable than traditional flash memory. So they have the potential to really revolutionize the data storage by offering faster write speed, greater durability, and higher data densities. The second area is the telecom, right? So in optical networks, reconfigurable photonic circuits using PCMs can significantly enhance the flexibility and efficiency of data transmission, so which is very crucial for the ever-increasing volume of internet traffic that we are using right now. The third area I think is going to be very critical will be the neuromorphic computing area. So they can emulate the behavior of biological synapses, making them essential for developing energy-efficient neuromorphic computing systems that mimic the human brain. So last one is just a little bit back up to what the question you asked earlier, energy efficiency, right? Because as I mentioned, they can operate with very low power consumption, so making them attractive for sustainable and energy efficient technologies.
So for all these applications, I'm sure there are other traditional materials being used now in this kind of devices for data storage, for telecoms, for neuromorphic devices, and energy efficient devices and all these things. So how do the properties of these kind of phase change materials differ from the traditional materials? I mean, what kind of advantages that they're offering, for us, you think of about replacing the traditional materials with these kind of materials. So what do they have?
Yes, great. So I think there are 6 main kind of differences. So the first one is in terms of bistability versus continuous variation. So for traditional reconfigurable switch materials such as MEMS or liquid crystals that we think about, they typically rely on mechanical movements or continuous variations in, say, alignment of molecules or movement of the parts, right, to achieve the switching. This can involve very slow response times and require power, constant power to maintain the switching state. But for PCM, because they have the bistability nature, right? So they can exist in either the amorphous or crystalline state. So once it's switched, the PCM remains in its state without continuous power. That's why we call it non-volatile, right? So the second unique property is in switching speed. So mechanical or molecular-oriented based switches often have slower response times because the physical nature of the switching process. You need, say, move the parts in MEMS devices, right, to introduce the delays. For PCM, the transition between the amorphous and the crystalline spaces in PCMs can occur in nanoseconds, allowing for much faster switching speeds. So this is very critical for high-speed memory and optical communications. The third one would be in scalability and integration. For traditional switching materials, such as liquid crystal, for example, they may face limitations in terms of the size and also integration with semiconductor technologies. So as an example, for the MEMS that we talked earlier, they require significant space, right, for the moving parts, limiting their scalability. But for PCMs, they can scale down to nanometer sizes, making them very, very good choice for integration with nanoscale devices. And also we can do a lot of integration, which is very critical for electronics and communications. Number 4 would be energy efficiency. Okay, so the continuous reconfiguration in traditional materials require sustained energy input, which can lead to higher power consumption. So this is particularly true for liquid crystal displays, LCDs, that require constant electric field to maintain the image. However, for PCMs, they are non-volatile, meaning that they can retain their state without needing the constant power. And this characteristic significantly reduces the energy consumption, making PCMs much more attractive in memory and logic applications. Number 5, durability and cycling. So for mechanical switches and some traditional electronic switches, they may degrade over time due to wear and tear from repeated cycling, right? Leading to reduced reliability. While PCMs they do undergo structural changes because you have to switch between the two states, but they're designed to withstand billions of cycles with very minimal degradation. So this durability is particularly advantageous in memory applications where frequent writing and erasing are required. So last one would be optical properties. So traditional optical switches may rely on materials whose optical properties change gradually. This will require complex modulation techniques to achieve desired effects. PCMs offer a very stark contrast in optical properties between the two states that they are in, providing very high contrast switching and simpler designs. So I think these are the 6 properties that I can identify.
Yeah. So at the beginning, you mentioned that these kind of phase change materials, their phases can be changed from amorphous to crystalline phases, depending by adjusting maybe the heat, the currents, or electric field or something. So by using that, you can change the phases of these materials. So are these is this going to be very robust? Because, like for example, you change the phase, you need something to hold the phase, right? So what is the robustness like? Like the accuracy of controlling the
PCM
face?
is a bistable, yeah, so I see that. So PCM is a bistable material. So once the phase has been changed, it'll stay in that state unless you provide another excitation to bring it back to the other state. So you don't have to maintain anything. It just stays in that state without you proactively, applying another excitation to switch back to the crystallization.
I see. And the change is abrupt, like a 0-1 kind of change, not like a smoothly.
There is a little bit. So we'll talk about extreme challenges later on. Is that they do have a little bit time for the switching process itself. So it depends on which phase you're going. A morphization process and a crystallization process, they take a little bit slightly different time. But we're not talking about long time. We're talking about milliseconds. We're talking about very short time for the switching between the two states. But once it's switched to the new state, it's stuck there basically, and you don't need to provide any power to maintain a state or anything. You only apply excitation when you want to bring it to another state.
I see. Okay, it's good. It's nice. At least I know a little bit more about it.
Yes.
So, since you're talking about the challenges, so what are the primary challenges in implementing these materials for reconfigurable switching, and what are people doing now, to address these kind of concerns? Yeah, the issues. Yeah,
of course. So obviously, I speak so highly of this material, and people say, "Why don't you do it?" Yeah, we want to, obviously, but it comes with challenges, right? So the first challenge is the precise control of the phase transitions to ensure reliable switching. So variation in temperature, heating rates, external conditions can lead to incomplete or inconsistent phase changes, affecting device performance. The researchers around the whole community are developing advanced material formulations and doping techniques to fine-tune the thermal and electrical properties to enable more controlled and uniform phase transitions. Additionally, techniques like localized heating using nanoscale heaters or laser pulses that's targeted to the specified areas to achieve precise control over switching processes has been done. The second challenge is material degradation and longevity, right? Because we're talking about structural change every time when you are changing the phase, right? So the repeated cycling between the two states can lead to material degradation for sure, such as atomic diffusion, void formation, or phase separation. So this degradation affects the longevity and the reliability of the device, of course. So to enhance the durability of PCMs, researchers are investigating on new materials with higher stability and resistance to degradation. So for example, their work on incorporation of robust elements or compounds that resist atomic migration is being explored. Additionally, people have done encapsulation techniques and the development of self-heating materials are being studied to mitigate the effects of cycling on the performance. The third challenge would be in thermal management. So the phase transitions in the PCMs is typically induced by heating, which can lead to localized hotspots and thermal crosstalk between adjacent elements in very densely packed device circuits. So effective thermal management is very crucial to prevent unwanted switching and ensure device stability. So researchers are working on improving the thermal conductivity within the PCM-based devices through the use of thermally conductive substrates or integrated heat sinks. Advanced designs that optimize the distribution of the heat and minimize the thermal interference are also being developed. And also low power switching techniques such as electrical or optical excitation are being investigated to reduce thermal loads, right? That's being introduced to the circuits. Number 4 challenge, I think, is in scalability and integration. So integrating PCM with existing semiconductor technologies and then scaling them for mass production pose significant challenges, right? Because we want to make sure the compatibility is there for with the standard fabrication process. So efforts are focused on developing fabrication techniques that are compatible with CMOS processes, such as sputtering or chemical vapor deposition for the PCM layers. They're also exploring hybrid integration, where PCMs are combined with other materials or technologies to achieve scalable and manufacturable devices. Next challenge, I think, also would be in the speed and energy efficiency. So the goal is always we want to achieve fast and energy efficient switching, especially like when we're talking about data storage and in photonic circuits. So the energy required to induce the phase change. So Rachel, you had this question just before this. They can be limiting factors. So to enhance the speed and energy efficiency, researchers around the world are exploring novel materials with lower switching energy and faster crystallization speed. Because between the two phase changes, the crystallization process takes a little bit longer than the amorphization process. So the idea is we want to make it a little faster. And also the approach is like we try to reduce the size of switching regions using nanowires or nanoparticles and optimize the pulse duration and intensity of the switching stimuli are also pursued to achieve a faster and more efficient switching. Last one is in environmental impact and sustainability. So some PCMs, particularly those based on chalcogenides, contain elements that are rare or potentially harmful to the environment. So when we're talking about concerns about sustainability of PCM technology, this is a big problem. So to address these concerns, researchers are investigating alternative materials that are more abundant and environmentally friendly. Organic phase change materials and bio-inspired alternatives are being explored. So you can see the whole theme with all these challenges really relies on new materials. How can we find a better material that can do the similar things that can make a better option for a fast and reconfigurable switching? So that's what I come up with.
I see. So looking for new materials is a very important, a crucial point in tackling one of these, one or two or many of these challenges.
Yes.
But another thing is because I have this concern as well about precise switching. How to make sure that the switch is like instant and abrupt, not like in a continuous, manner. So precise switching is important, and also the thermal management. So as I say, in the device, if you have heat and if you have more than just one part of the phase change happening, but if there's another adjacent one, so how do you manage the whole thing, the thermal conductivity in this case? And because it is thermal, that means it will affect the phase change of the materials. So it's very important to manage them well. Yeah. And then, scalability, and also do you mean it has to be CMOS compatible when you talk about integration?
Yes. Well, clearly you want to be CMOS compatible, right?
Yeah.
That's the whole idea, that you want to be CMOS compatible, and then you want to make sure that you can integrate to the whatever platform you're working on. Yeah, absolutely. You covered it completely correctly.
I see. Okay, good. Yeah. And so normally, can you give us some examples of materials, of this kind of phase change materials? So example, you mentioned just now chalcogenide and some organic materials as well. And can you give some names so that we have something in mind?
So right now, the key thing, I guess, at current state, majority of the community are using chalcogenides. So GSTs, right? GSSTs, right?
Yes.
And then, so people try to vary the exact composition of the GST material to make sure it's, with the good thermal performance, with the good switching performance. So the organic PCMs are newer. So people are trying to introduce other elements to replace the one of the GST component to see if they can do better. They can have a more longevity with the device, with the switching between. And then can we try to make the crystallization process a little faster with the other alternatives? But right now, at this very moment, chalcogenides are the primary solutions people are using. But clearly it has its disadvantages, right? So people are trying to see, can we do better?
Yeah, I see. Yeah, so obviously, phase-change materials are very attractive for reconfigurable switching because of their properties and all these things, the advantages that they're offering, and but they're also having lots of challenges ahead, to for them to overcome and all these things. So what are the future direction of research and development in this field? Like how are they? What do you foresee it's going to be? Yeah, for the future
You
of.
already summarized a lot of them, in my opinion. So I think the future, obviously, you can hear from what you just said, and then the summary that I gave about the challenges. The common theme is development of new materials with improved properties, such as low switching energy, faster transition times, greater thermal stabilities, right? So researchers are also exploring hybrid materials that combine PCM with other functional materials to create devices with enhanced capabilities. And also another promising direction is integrating PCMs with emerging technologies like 2D materials and nanophotonics, which could lead to ultra-compact and highly efficient reconfigurable devices. And there's also like a significant interest in exploring the potential of PCMs in quantum computing, where their ability to switch states with high precision could be used to control qubits. So I think in all we said here, advancing fabrication techniques to enable scalable production of PCM-based devices while maintaining high performance will be very, very, very big part of their future widespread adoption, in my opinion.
Yeah. So is this kind of work is remaining at the moment like research in the university, or but for the academia, interestingly, or it is something that is being done as well in the industry? So if this is a case, where like what role do the collaboration between the academia, industry, and maybe even government? We need funding, money.
Yes, yes.
And all these things to get further. So what are what role do they play here in advancing the phase-change materials for reconfigurable switching? I guess.
Yeah, so right now, obviously, the researchers like myself and everybody are still trying to get the best alternative materials. So we're still in the research phase. The widespread commercialization isn't there yet. So that's why we're trying to get there. So exactly as you said, collaboration between academia, industry, and government is very, very critical in advancing this field. So academia, like myself and other scientists, we provide fundamental research and theoretical models, right, to understand and optimize the processes. Then the industry drives the development of practical applications for commercialization, right? Then, as you also mentioned, government agencies, they provide funding initiatives and create policies that support innovation and then also adoption of new materials in, say, telecom, defense, and healthcare. So these collaborations can lead to the establishment of standards and best practices, making sure the PCM-based technologies are reliable, scalable, and ready for commercial use. And maybe partnership also is very good between the three. We can accelerate the transfer of knowledge from the lab, like research labs, to the market. So enabling a faster commercialization or deployment of the solutions.
So am I right saying that these phase-change materials, reconfigurable switches, are not yet commercially available? Not yet.
Not yet. Widely comparable. Maybe there is a small niche areas for people to use, but it's not, say, completely widely adapted in, say, your Apple computers. No, not yet.
Okay. Yeah, I think
we see the promises, we see the potential, and then we are hopeful that this is going to be a really excellent research direction going there.
Yeah. No, I think it is not easy. The route of commercialization for any research,
any new technology,
new research, to be brought out from the research lab out to the street
market.
Yeah, to the market is not easy. So I think your persistence and your endurance, in making this whole thing happen is very, very well applauded. Winnie, you have to keep up the good work.
I'm very hopeful that this technology will take over eventually in my lifetime.
Good. So, okay, so I think most of us know a lot about this, and it's quite interesting topic for me as well because it's very new, and I always think phase change materials can do many things. So I'm sure it is not only for reconfigurable switching; it can be for any other applications as well. So hopefully we'll see more out of them in the future. Yes, good. Thank you so much, Winnie, for
Thank
all
you
these
so much,
inputs.
Rachel.
Thank you. So, Akhil, back to you.
Thank you very much. That was absolutely fascinating. I've written down a lot of notes here. I think I'm going to stack them up and then see how much notes I've actually made. That was very interesting. Thank you very much, Rachel and Winnie. Before I let you go, Winnie, I've just got a couple more follow-up questions before we go. So my perspective as an early career researcher, somebody looking at a profile such as yourself, everything that you have done on the teaching side, on the research and innovation aspects, between mentorship, I had a few questions related to what young professionals might be curious about. So given the field that you're in, I'll start with a relatively technical question. If you had any students looking at building a research career or an innovation career in the field of PCMs, what do you think is the most interesting aspect of it to look at this stage?
It's a hard question to ask. Reconfigurable switching especially involves PCM. So Rachel has mentioned the many challenges that we have. So it is a cutting edge area where with a vast potential, right? There are a few key pieces of advice that I would offer. You should start by building a strong foundation in material science, photonics, and electrical engineering. So understanding the basics, the principles behind the phase transitions, the semiconductor devices, and optics will be very important as you focus into more specialized topics in the future. And then you need to engage in the research early on. So you should seek out opportunities to participate in research projects, such as in the PCMs, right? Whether through your university internship or collaborative initiatives. And then hands-on experience in a lab setting will really help you with practical knowledge that complements your theoretical understanding. And stay curious, right? This is the key. You have to keep yourself updated with the latest trends, the latest papers, attend conferences, read Nature papers, and engage with the scientific community. And then you need to really explore interdisciplinary areas such as nanotechnology, quantum computing, and neuromorphic engineering, because we said these are the future areas that will likely use PCM. So you want to know what you can contribute to these. So obviously, as you mentioned also earlier, Akhil, networking, mentorship, so important. You want to connect with professionals who are already working in this area at this moment, and you want to build a network of mentors and peers that can provide you with valuable insights, guidance, and opportunities, right? And I think maybe also you want to develop your problem-solving skills because we don't have a solution, right? As I mentioned earlier, there are lots of unknown solutions to the challenges we need to solve. So have a mindset that embraces challenges, and then you should be open to explore these new solutions because we don't have answers, but we want to try to find an answers, right? So that's my advice for
Fantastic.
newbies.
That's fantastic. And you also mentioned something that's a very good segue into our next question. Clearly, you've been an incredible mentor for a lot of students and a lot of peers within your community. So I was curious about that perspective of yours as well. Is that something that was very important to you in your career, or did that become important as you went along? What's your perspective on it?
So mentorship has been incredibly important throughout my own career, both as a mentor and then as a mentee. So when I was starting out, I was really fortunate to have mentors who guided me, offered advice to me, and opened doors to opportunities that I might not have discovered on my own. So their support really helped me navigate the complexities of academia and research. And also their encouragement really pushed me to pursue challenging projects that ultimately shaped my career. So as a mentor myself now, I find it equally rewarding to support the younger generation, the next generation of scientists and engineers. It's not just about sharing my knowledge or providing career advice. It's about helping the students and early career professionals to find their own paths, building confidence and develop their resilience needed to succeed in this very demanding field. So mentorship creates a ripple effect. What you invest in your mentees can have a lasting impact to yourself, because as they will in turn go on to mentor other people.
Absolutely.
So I
think that's fascinating. Can you share a bit more about that journey itself? Have you got an anecdote or a story or anything like that from your experiences?
Yeah, I think so. So mentorship really bridges the gap between knowledge and experience to provide a supportive environment where one can learn, grow, and make informed decisions. So for me, this has been a very continuous journey. So starting as a mentee, right, where I had to learn all the importance of asking questions, seeking feedback, and taking risks under the guidance of my supervisors, right, or my colleagues who have more experience than me. So one of the most valuable lessons I learned from my mentors is the importance of resilience. So because research, especially in the innovative fields like this, reconfigurable switching, often involves failures and setbacks, right? And my mentors taught me that these challenges are not roadblocks, but rather opportunities to learn and improve. They also emphasize the value of collaboration, encouraging me to work with others, share ideas, and build on collective knowledge. So from the perspective of being a mentor myself, I've learned that mentorship is not one size fit all approach. So each mentee is very unique with different goals, different challenges, and different learning styles. So effective mentorship involves active listening, understanding the individual's needs, and providing personalized guidance. Also, it involves encouraging independence. So mentorship is about empowering others to think critically and making their own decisions, making their own discoveries, rather than providing them with the answers. So, yeah, you have to understand, a lot of times we don't have answers. I don't know the solution to all these things, but I'm happy to try. So It's a two-way street, right? As a mentee, you gain wisdom and guidance. As a mentor, you gain new perspectives from your students or from your collaborators, and then you help each other to succeed. It's a mutually enriching experience.
And I think that's a very interesting perspective and a very interesting experience as well. I personally, for example, I've had an incredible mentor during my PhD. I've had an incredible mentor during my postdoc. Yet at my career stage, just starting out in academia, I'm also looking to mentor students of mine who are going to come through the academic line, but also I'm still searching for mentors because I've always got something to learn going forward as well. So wherever you are within your career and within the progress that you're having, you always end up either being a mentee or a mentor to somebody or the other. It's a two-way street for everyone, if that makes sense.
That makes perfect sense.
That's brilliant. So I'm going to shift gears now, and I'm going to ask you about some of the experiences you've had while you were building your career. Now, my involvement with the Photonics Society, I've worked previously with SPIE and Optica as well. Mm-hmm. Volunteering has been a pretty significant part of my career. Mm-hmm. So when did you start doing such activities, and do you have any idea of how that's impacted your career?
Mm-hmm. So I began volunteering early in my career, academic career as a graduate student. So I recognized that contributing to professional organizations like yourself, IEEE, Optica, SPIE, was not only an opportunity to give back to the community, but also a perfect way to grow personally and professionally. So I think volunteering for me allowed me to network with peers and leaders in the field, broadening my understanding of the challenges and opportunities with my community in photonics, and to develop leadership skills that I might not have required solely through my research and teaching. So the impact on my career has been super significant. Yep. So they helped me build a very strong professional network, which opened up collaboration opportunities and provided visibility for my work. It also deepened my sense of responsibility towards mentoring and supporting others. So the leadership roles I've taken on through volunteering have helped me to manage teams, make strategic decisions, and advocate for causes that I'm passionate about, such as women in engineering. So all of which has been invaluable as my career progressed.
And it's a very interesting way of also illustrating your leadership traits, your willingness to work with people. I think as you go through a PhD and a postdoc and you're in the early stages of your career, and this is independent of if you've done a PhD and you're going into industry, academia, if you're an early career young professional going into industry or into research, there are different ways of illustrating your personality traits. And I think volunteering gives you a platform to illustrate those sort of things. Would you agree with that?
Agreed completely.
Absolutely. Fantastic. I've got a couple more
Me
questions to
too.
go.
Me too. Me too. I agree
Exactly.
completely. Volunteering is very important. Yeah. It exposes you to many, many new skills that you never know. I mean, something that you will not get it inside the classroom. See.
Absolutely. And I think this is good for the listeners to know. This is happening completely organically. It has not been rehearsrsed. But my next sentence was going to be, I have 4 questions left, and I'd like to pull Rachel back into the conversation. So just like that,
I already
Rachel,
jumped in.
welcome back. I've got 4 questions remaining, and I think the idea is to see if I can pull a bit of information from your career, a bit of a knowledge bite, a bit of advice from both of your perspectives. You come at this from different perspectives, so I think your responses would be quite interesting as well. The way I'll do this, in the interest of the discussion as well, is I'll ask my question and we'll interchange between which one of you goes first. So in the first instance, Winnie, you can go first. The next question, Rachel can go first. What's the most important leadership lesson you've learned, and how has it been invaluable in your career? So Winnie first.
Okay, Rachel, I'll take this one first. So the most important leadership lesson I've learned is the power of empathy and active listening. As a leader, it's easy to get caught up with decision making and driving projects forward by yourself. But it's crucial to take the time to understand other perspectives, challenges, and aspirations from your team members. So that's mine.
Fantastic. Rachel?
Winnie, you have said everything I wanted to say. No. I think listening skill. I mean, listening is very important. To be a leader, you need to be able to listen and then to understand any issue and all these things from other people before you make a decision on how to proceed, how to solve the problems. I think listening is very important. And I think another one is dare to take risk as well. I think as a leader, because it is your call sometimes to make a decision. Like, for example, in what I'm doing as an editor in publishing, we need to make decision whether, to go ahead with a publication or maybe to make a decision to cancel a project and all these things. So we need to be able to take the risk. But when I say risk, I'm not saying any risk. It's an informed decision. Make an informed decision. Yes. Yeah. And then just go with it, and then be brave with what you have made and achieved. Yes.
I think the interesting thing about most work environments is the occasional risk that you take is actually building experience, it's building knowledge. So it's never completely wrong. It's always good to take that odd risk every once in a while. So my second question, if you could give one piece of advice for somebody in the early stages of their career, now think about somebody who's just graduated an undergraduate, a master's, or a PhD course. They haven't decided if they want to go into industry, into public policy, into engagement, into research and innovation, academia. What would your advice be to that person at that stage?
Okay. I think it is very important that as a young master degree holder or a young PhD degree holder, you need to think a little bit outside the box, about what you want to do. I always say to people that a degree is just like a passport. It's a passport for you to get to a place. And then you try to make use of that passport to do what you always want to do, what you always love to do. And then that is nice life, So
Absolutely.
think out of the box. Yeah, when you're thinking about which career to pursue, importantly is to follow your passion. Follow your passion and use the degree as a passport to achieve what you want. Yeah, and don't be restricted with for example, maybe a piece of advice from a supervisor, be a researcher, or stick to one thing. No, just be open. Yeah.
Fantastic. Winnie?
Yeah, to Atom was excellent advice. So I think, first you need to really do a really honest evaluation of yourself. What are you interested in? to really choose your career path first. So are you more interested in research and then thinking about a future and then directing students to help you, or are you really, you love the dynamics in working industry, the excitement in delivering a commercial product, right? So you decide what really make you passionate about, like exactly what Rachel said. And then once you choose your path, you have to understand in any career path you choose, there are going to be challenges for you. And you need to really not be afraid of the challenges. You don't want to, hide from the challenges. You want to lean into them with curiosity and resilience and try to solve the problem. Each challenge you face is a chance to learn, to improve, and to build your confidence. So don't be afraid to ask for help or advice from mentors and colleagues. And also just really use the help you can get to navigate through your career path. And then, and then you have to remember your career is a journey, not a race, right? So you take your time to explore what you want, learn new skills, and figure out what truly excites you.
Absolutely. I think the passport idea and exploring new avenues is extremely interesting, because one of the key pieces of advice that I actually got in my career when I was doing my PhD supervisor would constantly say, don't look at this as the highest academic degree you can get. Think about this as training for the rest of your research career. And that perspective was really, really helpful for setting the pace. So another question that I get asked quite often, and obviously I'm sure you get this question much more than I do, given where you are at your career stages as well. Would you recommend somebody to diversify their research skills, their expertise, sort of understand a substantial amount about a lot of things? Or would you say that somebody should become an absolute expert at a very, very narrow topic? Which perspective do you hold?
Yeah, sure. From my perspective, both approaches have their merits, and the best path often, in my opinion, depends on their career goals and the field they're in. However, I really believe that early in your career, it's beneficial to diversify your research experience with skill sets. So you want to engage yourself with different topics, different methodologies, different disciplines can really provide you with a broader perspective and a more versatile skill set, right, which is valuable in today's interdisciplinary research environment. But when you are in this diversified area, you can explore, various different parts, and then maybe you'll discover new interests or identify new or unique intersections between fields that can lead to innovative research directions. Additionally, a diverse skill set can make you a more adaptable and resilient in the face of changes of the job market or the research funding trends right now. But once you gain a solid foundation and then identified a particular area of interest that you want to pursue your career with, then you can choose a specialized area and develop a deeper expertise in that niche. So this combination of broad experience and focused expertise can really position you as a well-rounded, flexible, and innovative scientist. So that's my perspective.
I think that's very interesting, because the diversity of skill sets and the diversity of knowledge has a very, very big value. This is something that I relate to quite a bit from my perspective, because from my undergraduate, master's degree, PhD, and my postdoc, I've done different topics at each of these stages. So when I actually now approach a problem statement, or I write a grant application, or I write a paper, the background really helps, because I know quite a bit about quite a lot of things. So it's nice to piece the whole puzzle together in order to actually make it work. So my final question for today: what would you say are the key attributes or qualities of young scientists these days, the ones that you find in your experience are quote unquote successful? What are the qualities that they seem to sort of project, and what are the things that you think more young scientists should get themselves trained in?
I think, to me, young scientists, early career researcher should be brave. Yeah, brave in terms of taking a new research direction, not listening to supervisor all the time. Yeah, and also be brave in approaching to like leaders in the research, in any research field. Brave in approaching them, to talk to them, to introduce them to you. I mean, about yourself, to introduce yourself to them, and then to tell them about your research, to make yourself known to the leaders in the field. I think it's very important because impression is very important here. I'm not talking about asking for collaboration or something. It's basically to make them know about you and your research. So be brave. I think this will make you successful for whatever that you're doing, not even just for your career, but as a person. Yeah.
Absolutely. And Winnie?
Yeah, I think having a passion, right? Remain curious. You want to continuously learn and seek to ask questions, to explore new ideas, and then to really have that motivation in you, have that fire in you that you want to continue to do that. And as Rachel was saying, that research is hard, right? We don't have solutions. That's why it's called research. So when it is very hard, when it's very challenging, when everything is unpredictable, just stay there and then just being strong, being strong to yourself, and then be true to yourself, being resilient to the setbacks, to the failure, right? And then you just try to really look for the long-term success and look for mentors, right? So getting help from others, communicate with your peers, and getting new ideas. Yeah.
I think it's very interesting from this side of the table, sort of listening to your feedback. I think it's very interesting for people to note that none of the things that we've talked about in terms of personality development have anything to do with the science. It's not about scholarly ability. It's more about put yourself out there, be brave, ask questions, engage with people. It's very interesting that in today's knowledge-driven world, I think we're in a scenario where personalities get an opportunity to shine because so many people are doing such incredible work.
Right.
It's just put yourself out there and make yourself known. I think that's a very, very interesting takeaway. So thank you very much, Rachel. Thank you very much, Winnie. This has been an absolutely fascinating conversation. We've talked about PCMs. We've gone into technical details. We've talked about innovations, challenges. We've talked about empathy and leadership as well. We've talked about career development. We've talked about professional development. We've covered so many things in today's conversation, and I think this has been an incredible discussion. I'm sure everyone at the other end has enjoyed this as much as I have, and in the future, I think we'll definitely try and do this again at some point. But best of luck. Congratulations for all of your success, Winnie. It's very nice to see you again, Rachel, and I'm sure we'll meet again at a conference in the future. So thank you very much. Thank you, everyone.
Thank you very much. Thank you, Rachel. Thank you, Akhil. Thank you, Kristen.